This is Jack Jackson with Probability Lectures Part 6 on multistage probability and probability trees. We're going to begin by defining a random variable in a probability distribution, at least in the discrete case. A random variable assigns a unique number to each event from a sample space. So notice that these events are not necessarily simple events, nor are they automatically equally likely. A probability distribution function or probability density function, we'll abbreviate that PDF, assigns a probability to each value of the random variable. When we're dealing with the discrete probability distribution function, then we're going to have a finite number of these, or at least a countably infinite number of probabilities, and all these probabilities must add up to 1, as we usually get with the probability situation. So notice that the random variable represents the output of the function from the set of events to the set of real numbers, but it's the input of the probability distribution function. So we have a composition going on here where we start with the sample space and we take those things and we give them a number, a value of the random variable. It's an output of the random variable there. It's the output of that function. But then that random variable then becomes the input for the PDF. So let's look at some examples. We've already seen an example of a random variable already. So take the experiment where we roll a standard fair die and let the random variable x be the number of dots on the top face. So we can make a table of all the possible values of x and their probabilities, and then make a bar graph of these probabilities, and that would be called graphing the distribution. And notice the graph of a discrete PDF is a bar graph. Go ahead and do that now. Press pause right now. Okay, well, I'm sure this was no problem for you. We know that the probabilities are all the same. They're all 1/6. Notice they do add up to 1. And the distribution probability density function, when we graph that, is just a what we call a discrete uniform distribution. So they're all the same height. Now let's get a little bit more interesting. Let's get a multi-stage example. Suppose we roll a pair of fair dice. Let x be the random variable that's the sum of the total number of dots on the top faces of both dice. So in other words, in the example we have here where we roll a 6 on one and a 4 on the other, the sum is 10, so x equals 10. So what's the probability that x is 5? In other words, the total of rolling a 5 with 2 dice. What is that probability? Go ahead and figure that out right now. Press pause and figure that out. Come back when you've got it figured out. Please press pause now. Okay, this is a little bit more difficult, isn't it? We did this in class recently with a class of students, and these are answers that they came up with. They came up with a third, a fourth, 1/5, 1/6, 1/7, 1/8, 1/9, 1/11, 1/12. And here are percentages that go along with those, at least approximately. And, well, which one's right? Are any of them right? I guess what we see is, while it was pretty obvious when we were just rolling one die, it becomes not quite so obvious at all when we do something very simple, really, and that's just rolling a pair of dice. So maybe it's not so obvious what's going on here. Actually, only 2 people had the correct answer. So the correct answer is in here, but only 2 people out of 20 got that right. So what are we going to do here? Well, one thing we might do, just to see which one's reasonable, is to do an empirical probability. If you remember, that is, we're just going to do an experiment, and we're going to do a simulation where we repeat this experiment over and over again a bunch of times and see what we get. So what I'd like you to do now is actually get you a pair of dice and actually roll them 100 times, and each time record what x is, the sum of the total number of dots on the top faces of both dice put together, and record that each time you roll the pair of dice, and roll these pairs 100 times and record your results. Make yourself a frequency table, a relative frequency table, and then a bar graph of these empirical probabilities, that is, these relative frequencies. And then based on what you see which one of those answers see if your answer you came up with seems reasonable with this, or if any of those that the students came up with in class seem like they might be reasonable based on those experimental results. Of course, you can use some virtual version of rolling the dice if you don't have the actual physical dice, for example, the dice roller on your calculator, or perhaps some kind of computer simulator. But go ahead and stop this, and then we'll do this experiment and then come back. Press pause now. Well, I had a group of students do this in class as well, and collectively they did this experiment 700 times, and they came up with 13 times they came up with a total of 2, 39 times they came up with a total of 3, and so forth. You can see the totals that they came up here. These should add up to 700. And then the relative frequencies, 13 over 700, approximately 1.86%, and so forth. All of these are just these numbers over here, the frequencies divided by 700. So the relative frequencies, of course, should add up to 1. And then here's a graph of that right here. It's a frequency histogram. Actually, it's a relative frequency histogram. So based on this, which one of the results seem reasonable? Well, let's find 5, 9.57%, this bar right here. I actually noticed something interesting about this. They weren't all the same. Okay? In fact, we noticed it was pretty rare to get either a 2 or a 12, but a 7, for example, was very common. It happened about 16% of the time here. And then things kind of trailed off on either side of that. So that's kind of interesting that these are not equally likely outcomes. And that's part of the problem why this is harder to count. If they were all equally likely outcomes, everything would be 1/11th because there are 11 different possibilities. But it doesn't look like 1/11th is a reasonable choice here because we're definitely not getting flat across even bars. It's a little harder to get the ones out towards the extreme, a little easier to get the ones in the middle. So if we look here, these are the examples of the possible answers the students came up with, and of the ones that are closest to this 5, 9.57% would be the 1/11th and 1/9. Those seem to be pretty close, so those could be possibilities. Maybe even the 1/12th or the 1/8th, but there's no way these are just getting too big. So it looks like our experimental results say that these down here, 1/3, 1/4, 1/5, 1/6, 1/7, that these guys down here are a little bit too big based on our experimental results. Looks like they're too big to be the real probability. So maybe the real probability is somewhere in here. Well, how do we figure out that real probability? Well, first we want to make a list of all the x values and their probabilities eventually. But if we do the x values, well, that part's pretty easy. We can get a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nothing in between this, nothing below a 2, nothing above a 12. So that's pretty easy, but the problem is these are not equally likely. Now, probability concept is very simple. You just take the size of the event divided by the size of the sample space. What's hard in this case is counting. It turns out counting is not quite so easy. You may have thought just counting stuff was pretty easy back in your elementary school days, but as we're getting in this course, we see that there are some things that are a little bit harder to count. So we need a way of counting this so that we can figure out what the simple events are and how they map up to the random variables. So what we really need is to make a list of all the possible dice rolls that lead to each value of this. So let's take a minute and we'll stop the video here and you figure out how many different ways you can get each one of these different x values. What dice rolls will actually produce that. So go ahead and figure that out now. Please press stop now. Okay, now we're back. Let's see what we came up with. How many ways can we roll a 2? Well, yeah, there's only one way. Both dice have to be on the 1. How about a 12? Yeah, only one way to do that. Both dice have to be a 6. Sometimes they call the 2 a snake eyes, and sometimes they call the 12 boxcars. But either way, there's only one way of each of those. Okay, let's do one that's a little more interesting. How about a 3? How many ways can we get a 3? Okay, did you say they have to be a 1 and a 2? But now here's another issue. Does that 1 and a 2, does that count as 2 different things or as one thing? How do you count that? And why? Well, it actually counts as 2 possibilities. One way you can see this is think of each die as a very specific thing. It is a very specific thing. And to identify them, we might, identify them somehow. For example, we might actually use 2 different colors of dice. So, for example, we might have a white die and a red die. We can get a 1 on the white die and a 2 on the red die, or we can get a 2 on the white die and a 1 on the red die. So if you think of this as an ordered pair, then there's 2 ways of rolling a 3, either 1 and a 2, or a 2 and a 1. And those count as 2 different things. Okay, now let's go to 4. How many ways can we get a 4? Did you get 3 ways, or did you get 4 ways? Or did you get something else? Well, there's actually 3 ways. A 1 and a 3, a 3 and a 1, and a 2 and 2. Now notice the 1, 3, we can reverse the dice to get a 3, 1. A 1 on the red die and a 3 on the white die can be reversed so that we can change the 1, the red die, from a 1 to a 3, and the white die from a 3 to a 1, and that gives us still 4, but a different way of arranging the dice. But on the other hand, 2, 2 only counts once. Reversing it doesn't change the ordered pair, and you can't actually get a new thing by reversing it because you're not changing in either one of the dice to get that to work out. So that's only counts once. So we have a total of 3 ways: 1, 3, 3, 1, and 2, 2. Let's skip ahead all the way to the whole sample space. How many different rolls are there altogether now? Think about how we're counting these. How many would there be altogether? Well, there are 36 rolls, and each one is, at this time, these are simple events, and they are equally likely. So if you think about that, we have 6 choices for the first die, say the red one, and for each one of these, there's 6 different ways we can arrange the second die. So that's 6 for every 6. So that's 6 times 6, or a total of 36 total possible rolls. So the sample size has size 36. Here they are. Here's all 36 rolls. Notice this one is the one that has 2. These 2 across this diagonal are 3s. Across this diagonal is 4s, 5s, 6s. 7s are right down the center diagonal here. Then 8s, 9s, 10s, 11s up here, and 12 here. So go ahead and fill out the chart for the probabilities now of the dice rolls. Press pause now. Okay, now that you're back, let's take a look and see if you got this. So here's the actual dice rolls. We can see all the different possibilities here. And the actual rolls are here in the middle. And the x value, the random variable, is over here. The number of dots on each row is over here on the left. And if you look, the probabilities are over here. Out of the 36, we have 1, 2, 3, 4, 5, 6, and back down to 5, 4, 3, 2, 1. And so the probabilities are 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, and so forth. So in particular, the probability of 5 would be 4 over 36, which reduces to 1/9. So here are the fractions, the same fractions now, in reduced form right here. So we have the x's and the probabilities in fractions form that's reduced, and then a decimal form rounded off to 2 decimal places here for each one. And here's the actual graph of the PDF. This is the actual graph of this probability distribution, this probability density function. Again, down here we have the number of dots. This is our x value. On this scale we have our relative frequency, whether that's a fraction or a percent. I've got it in percent form over here, and we've got at least approximate percentages here as well. Notice if we compare that to the empirical data that we have, we do see that our empirical data was pretty close, right? And of course we wouldn't expect it to be right on, but sure enough, right there in the middle at 16% was close to the 16.7%, which it should be for 7, and then sure enough it drops a little off on each side, trailing off to the ends. And so the real probability of phi was 11.1 repeating percent, or 1/9, and our estimation based on our experiment was 9.57%, so it's not too far off there. So the folks that said 1/9, those 2 students, they got it right. Let's do another example now. Suppose we're going to do the experiment of having 2 children. It's quite an experiment, let me tell you. I have 2 myself. Let the random variable x be the total number of female children. Make a table of all the possible values of x and their probabilities that go with them. In other words, make the table for the PDF. And then also make a graph, which will of course be a bar graph for this PDF. Go ahead and do that now. Press pause now. Well, before we go back to this, let's review a little bit of something that we had done earlier. In one of the earlier videos, we talked about conditional probability and how that leads us to a multiplication rule. And so remember, the conditional probability of A given B is probability of A intersect B over the probability of B. But if we multiply both sides of this equation right here by B, probability of B, we get an expression for the probability of the intersection of A and B. In other words, the probability that A and B both happen. That's the probability of B times the probability of A given B. But in a similar way, we can look at this expression on the right and get probability of A intersect B. It's probability of A times probability of B given A. This gives us a way to find probabilities of intersections if we know the probability of the first event and then the probability of the second event, how it happens given the first one. That's going to be useful to us in this example. And that's going to lead us to something that we call a probability tree. And the probability tree here, we see this on the left, we start at the beginning and we have our 2 branches. We have the event M1 and F1. That is, M1 is that there's a male first child. F1 is that there's a female first child. Each one of those has probability of 1/2. Then what we put on this next one, once you've had a male child the first time, you could either have a male or a female child the second time, M sub 2 or F sub 2. And so what we have on this branch here, notice we put probabilities on this branch. Either one of these original branches was probability 1/2. And by the way, if there's coming from a node here, these must add up to 1. So these are called, actually this is usually called a vertex. If you're coming from the vertex out of it, all the probabilities must add up to 1. So here we have probabilities coming out of here. Well, again, this is the probability. The only way you get here is if you already had the male first child. So this is a conditional probability. The probability that we have a male second given that we had a male first. This should be probably M sub 2 given M sub 1. And that's 1/2. This is probably F sub 2 given M sub 1. And it's also probability 1/2. Likewise, the probability of a M sub 2 given F sub 1 is 1/2, and the probability that they're both female at this point is that we have a second female given we had a first one is 1/2. So all these probabilities are 1/2. Now what's the probability that you had a male on 1 and 2? Well, remember, we can multiply these probabilities. It's the probability of male 1, this one here, times the probability of male 2 given male 1, which is here, which is also 1/2. So it's 1/2 times 1/2 is 1/4. So notice to get the probability that we went on this path from the beginning to the end, male then male, was we're multiplying the probabilities along the paths. Each probability here is a conditional probability under the condition that everything on the path earlier has already occurred. The probability of male and female, that's the intersection of M1 and F2, those events, it's the probability of male 1 times the probability of female 2 given male 1. And so that is 1/2 times 1/2 is 1/4. Similarly, these are all 1/4. So we have 4 events: male male, male female, female male, female female, and each one of those is actually equally likely at 1/4. Now the random variable 0, 1, or 2, those are not equally likely. We have a 1/4 chance of getting 0 females. That's this top branch, male male. That's the only one. That's 1/4. And then we have probability of 2. That's only the bottom branch, female female. But for the middle one, for 1, we have 2 branches. We can go female male, or we can go male female, each with a probability of 1/2, and those add up to 1/2. So we have 1/4, 1/4. They add up to 1/2. So notice we have 4 probabilities, each of 1/4. These probabilities at the end are mutually exclusive. These events are mutually exclusive. So if you have male first and male second, you're not going to have one of these other possibilities. So remember, when we have mutually exclusive events, we should be able to just add up those probabilities to find the union probabilities. Of course, if you union all these events, you've taken care of every possibility. So it better add up to 1. So these probabilities on the outside must always add up to 1, and sure enough they do. Here they are in percent form, and here's a graph. So if you think about it this way, then there's a 50% or 1/2 chance that you'll have one child of each gender. 1 out of 4 families will have 2 males, and 1 out of 4 should have 2 females. You can also answer other questions like, what's the probability that they have at least 1 female? Well, add these together, 75%, or 3/4. Let's go on. Okay, so let's extend this idea and make it a little bit more challenging. This time we have the experiment that you have 4 children. This time a random variable x, once again, will be the total number of female children. So, this time I want you to make a probability tree. Be sure you label all the probabilities along all the connecting edges. Label the vertices as male or female, and then figure out the probability of each path from the beginning to the end. Use that to help you figure out the table for the PDF, and also graph the PDF with a bar graph. Please do this now. Press pause now. Well, if you look at it, this is what you're going to end up with. First child, male or female. Then you have male or female the next time. Each time you have a male or female branch. Notice we're going to end up with a total of 16 branches, all equally likely, so they're all probability 1/16. And again, you can find those probabilities. 1/2, this should say 1/2 there, 1/2 and 1/2. So you multiply these together, 1/2 times 1/2 times 1/2 times 1/2 to get 1/16. This probability is just the probability that you have male first child. This is actually the probabilities, if it says 1/2, is the probability that you have a male second child given you have a male first. This is the probability of a male third child given that the male childs were for both first and second child. And this probability here is the probability of a male child on the 4th time given that the first 3 were male. These are actually, we'll talk about this more in our next lecture, but these are actually independent events. Each child is independent of what happened earlier. So the probability for a male and a female each time is basically 1/2, at least very close to 1/2, and so we're going to go with it being 1/2. So these probabilities are all 1/16 for each of these outcomes. Actually, these are simple events, all 16 of these. Now, our random variable, remember, is going to count the number of girls. So number of female children. So that's could be 0, 1, 2, 3, or 4. And the red number down here is the only possibility of 4 females. Female, 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 female. That's the bottom branch all the way around. That's 1/16. The one at the top, all male, 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 male. That'll be no females, and that's the only way you get no females. That's 1/16. Now the purple ones, here, this one, this one, this one, and this one, all have 3 females. Male, then 3 females. Female, male, female, female. Female, 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 male, female. Female, 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 male. Okay, so I have 4 of those 16ths I add up, and it becomes 4/16. Let's do the green ones next. 1 female. Okay, so that's going to happen 4 times as well. It's the 4 green ones here. Boy, 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 girl, boy, boy, girl, boy. I think these are switched in colors. It should have been this one is green. Then boy, girl, boy, boy. That one's green. Not this one. These 2 are switched colors. And let's see, this one here, girl, boy, boy, boy. And but the total's right. There are 4 of those, so that's 4/16, which reduces to 1/4 or 25%. The brown ones should be this one that was switch color. Where is it? This one here. Boy, boy, girl, girl. That's 2 girls. This one, and then boy, girl, boy, girl, boy, girl, girl, boy, female, male, male, female, female, male, female, male, female, female, male, male. So those are the ones that have 2, and there are 1, 2, 3, 4, 5, 6 of those. So that's 6/16, which reduces to 3/8, or 37.5%. And again, these should all add up to 1, and they do. And so you can see the graph there. So again, the most common thing would be to have, in 4 children, would be to have 2 females and 2 males. Even split, that happens 3/8 of the time. But at 1/4 of the time, you have 3 females and 1 male. Also 1/4 of the time, the other way around, 1 female, 3 males. And about 1/16 of the families with 4 children will have all girls, and about 1/16 will have all boys. Alright, I hope that shows you how the tree can help us really keep track of things a bit. So let's try another example. Suppose we just got an urn or some kind of container, and it has 8 red balls in it and 4 blue balls in it. That's all it's got. We're going to shake them up, mix them up really good, and draw a ball at random from each urn. Okay, but we're going to do this 3 times, and each time before we draw the ball, we're going to put the ball back, shake it up, and draw again. So each time we're going to be drawing from an urn that has 8 red balls and 4 blue. So this is called with replacement, because we're replacing that. Okay, that's going to be important for us. We're going to consider again the same problem in a few minutes when we don't replace it, and you'll see that it makes a difference. So let's let X be the total number of red balls that we draw out. Of course, what could X be? What are the values X could take on? Well, it could be 0, 1, 2, or 3. So there are actually 4 different possibilities: 0, 1, 2, or 3. So make a probability tree with all the probabilities, make a table, and graph of the PDF. Do that now, please. Please press pause now. Well, here's our probability tree this time. Okay, and so we see that there are 12 balls in their total, 8 blue, 4 red. So the probability we draw blue on the first one is 8/12, or that reduces to 2/3, and then it's 4/12, or reduced to 1/3, is the probability we draw a red ball. Now, given that we've already drawn a blue one the first time, we're putting the ball back. So again, the second time, it's 2/3 that we draw a blue one, and 1/3 we draw a red one, 4 out of 12 for red, 8 out of 12 for blue. And again, when we draw the third one, again, the same numbers. So each time we have a branch here, we're going to put the 2/3 going to blue on the top and the 1/3 going to red on the bottom, coming out of each one of these. So each time we're going to multiply these out. So if we looked at the reduced versions, the denominators are all 3. So we got 3 times 3 times 3 on the bottom is 27 for the denominator each time. And then we just have to multiply the numerators. We're going to use the reduced version. So 2 times 2 times 2 is 8. So this is 8 27ths is a probability that they're all blue. Okay? Which means there's 0 reds. So that's 8 27ths. That's the only way to get that one. Let's look at all red the other way. 1/3 times 1/3 times 1/3 is just 1 over 27. So there's probabilities 1/27 that will be all red. That's the only path that has all 3 red. Now we have some of these that with purple numbers at the end, and these should be the ones that have 2 reds in them. So every time it's got 2 reds, let's see what happens. The denominators again are 3, 3, and 3. So it's going to be 27 for the denominator all the way up and down. So what about the numerators? Well, this is going to be 1, 1, and 2. 1 times 1 times 2 is 2. So that gives us 2 27ths. Okay, at least for this one path. 2 27ths that we get a red, red, blue in that order. But we could also do red, blue, red. It's also 2 27ths. Look at what we have. All the denominators are still 3, so it's still 27. Our numerators are the same numbers in a different order. 1, 2, and 1. So it's still 2 27ths. And there's one more up here that's also that way. It's also 2 27ths. Again, the denominators are all 3, 3, and 3, at least the reduced version. For 27, the numerators are 2, 1, and 1 again, so it's still 2 27ths. But we have 3 of those. Multiply that by 3, we get 2 ninths. And so we get 2 ninths is the probability of having 2 red balls drawn. What about 1? Well, there's also 3 of the past that turn out to be that. That's the ones with the green. It turns out they're all probabilities of 4 27ths. Again, the denominators are 3, 3, and 3. 3 times 3 times 3 is 27. The numerators are 1, 2, and 2. 1 times 2 times 2 is 4. And that's true for every one of these that are green. And so we get 3 of these 4 27ths. 4 27ths plus 4 27ths plus 4 27ths is 3 times 4 27ths, which is 4 ninths. And so the probability that you get one of those is 4 ninths. Okay, notice that these probabilities are not changing when we do it with replacement. And also notice there are multiple paths that lead you to the same x value. So we're adding these up. And that's also looking at what these probabilities are. So let me just follow a particular path. This probability, 2/3 or 8/12, is a probability we draw blue. This path here is the probability that we draw red the second time, given that we drew a blue the first time. And since we put the ball back, it's still 1/3. And then this is the probability here that we drew a red the third time, given that we've already drawn a blue the first and a red the second. But again, we're putting the ball back, so these probabilities are independent of what's happened earlier. Every time we draw a red, that has a probability 1/3, and the probability we draw blue is 2/3. And you get a look at the histogram there. Notice that a 1 is the most popular thing, followed by 0 and 2. And finally, 3 is pretty rare. Now let's change it up. Let's do exactly the same experiment, except this time, when we draw that first, shake them up, pull out that first ball at random, we're not going to put it back when we draw the next time. So the first time we're drawing out of a total of 12, but the next time there's only going to be 11, and there's going to be one less, either blue or red, depending on what we drew the first time. So now our new probabilities are no longer independent of what we drew the first time. It's going to make a difference which one of these was being picked the first time. That's going to affect the probability from there on. So once again, we want X to be the total number of red balls, and we want you to make a probability tree with all the probabilities, a table of the PDF, and a graph of the PDF. Let's do that now. Please press pause now. Well, here's the tree for this example. Starts out the same as last time. 8/12 that you draw blue and 4/12 that you draw red. But now look what happens. We started with 12 balls. If we draw a blue one, that has a probability of 8/12 because we're drawing one of the 8 from the 12. But once that blue one is drawn, now we only have 11 balls. 7 are blue and 4 are red. So the probability of a blue second time given a blue the first time is 7/11. If I really wanted to be correct, I should call this blue sub 1, B sub 1 for blue the first time, and B sub 2 for blue the second time. Two really different events. Okay, but we just kind of got a little bit easier by just saying blue. Okay, so this is a blue the second time, and notice we're saying if to get here you have to have already had a blue the first time. So this probability here, 7/11, is the probability of drawing a blue one given that we drew a blue one the first time. Probability of blue on the second draw given that we had a blue the first. This 4/11 is the probability that we drew the red given that we drew a blue the first time. So actually by drawing a blue one here, we've decreased our probability of a blue the second time compared to the first, but we've increased the probability of a red the second time. Next time down the road here, this blue here should be blue sub 3. This probability, 6/10, is the probability of a blue the third time given we had a blue the first and the second time. So by now, 2 blues are gone, so we're down to 6 blues, and the total of 10 there. And that leaves 4 reds out of 10, so 4/10 for the probability of red. Once again, coming out to the right here of a vertex, the probability should sum to 1. 6/10 plus 4/10 is 10/10, which is 1. Coming out of this one, 7/11 plus 4/11, that's 11/11, that's 1. Even at the very beginning, 8/12 plus 4/12 adds up to 1. So any of the things going to the right should add up, all the probabilities add up to 1. In a similar manner, we fill out the rest of that. Okay? Now, to find the probabilities here, we can multiply. We can multiply the probability of B times the probability of, let's say, probability of B1, times the probability of B2 given B1, times the probability of B3 given B1 and B2. So we can multiply probabilities along these paths. And when we do that, we always have a denominator of 12, 11, and a 10. We're going to get some canceling here, but that's the denominator. And the numerator is 8 times 7 times 6. After you reduce that down, that turns out to be 14/55. In a similar manner, we can find the probability of going here. That is blue, then red, in that order. So we're multiplying 8/12 times 7/11 times 4/10. So we're multiplying these three probabilities together, reduce that to 28/165. All three of the green ones turn out to be 28/165. They have a 4, a 7, and an 8 in some order in the numerators. And the denominators, all the denominators are 12, 11, and 10 multiplied together before we reduce. In a similar manner, go ahead and fill out the rest of this. Please double check this and see that you get these probabilities in the table and at the end. Now, to fill out our chart for our probability density function, our PDF, we list all the values of x, which remember x was the number of red balls, so that's 0, 1, 2, or 3. 3 is only down here, which is 1 out of 55. 2 happens several places. That's all the purple ones. 2 reds and a blue, red, blue, red, blue, red, red, blue, blue, red. No, not blue, blue, red. That's it. Red, blue, red, 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 blue, blue, red, red. The 3 purple ones. So that's 3 times 4/55 is 12/55. That's 21.8%. And then finally we have the green ones, which are the ones with just one red, and that's 8/12 times 7/11 times 4/10. Again, we have 11 times 10 times 12 for the denominator, and then the green ones all have the numerator of 8 times 7 times 4. And so they are all each 128 over 165. We multiply that by 3, we get 28 over 55.